the faith in the technology, it's the faith in the people. Good evening, everyone present here. I, Sarthak Arora, a first year student at BITS Pilani, on the behalf of the Computer Science Association, warmly welcome Dr. Divyakant Agrawal, the batch of 1980, BITS Pilani. Dr. Agarwal is a professor of computer science at the University of California, Santa Barbara. His research interests involve databases, distributed systems, cloud computing, and big data infrastructures and analysis. He is the fellow of the ACM, the IEEE, and the AAAS. He also serves as the editor-in-chief of the Journal of the Distributed and Parallel Databases. Moreover, he has also served on the editorial boards of IEEE Transactions on Knowledge and Data Engineering, ASIM Transactions on Database Systems, ASIM Transaction of Spatial Algorithms and Systems, and ACM Books. His publications include 400 plus articles on databases and distributed systems, and he has supervised over 35 PhD students during his tenure at the University of California. Adding to the accomplishments, Dr. Divyakant is also the recipient of the UCSB Academic Senate Award for Outstanding Graduate Mentoring. Handling the stage over to Dr. Divyakant Agrawal.
Okay, thank you, Sarthak. So let's just make sure. So you guys can see my presentation now? Can you guys hear me?
Yes, sir, it's visible.
Okay. And all right. So I thought before I begin, I'll just give you guys a little bit of a background as to my journey. So my early years were primarily spent in Madhya Pradesh. My father was a judge, and he got transferred in multiple locations. So I'm a product of 6 different schools, culminating in the higher secondary school in Sector 10, Bhilai, which is, I think, somewhat known. And my undergraduate education was at BITS, and I think it was 5 glorious and formative years. So one of the highlights, I don't know how much you guys know about the history. At the time when I came to BITS, the director of BITS was this person called C.R. Mitra, Dr. C.R. Mitra. And I think he is now, considered one of the great educationists of his time. And he had instituted this plan of integrated 5-year undergraduate program. So when we entered BITS, we entered as being an unassigned students. And the idea was, as we advance through our education, we will branch out to different specialization. So the Mitra's vision was he wanted to create an undergraduate engineering degree which was very broad based, so that the products can go out and start doing things. So for example, I seem to remember doing courses in transport phenomena, materials, and so even though my interest was electrical engineering, I was doing much more broad-based studies. So it was, I think, a very interesting experience. But more importantly, what it did was, from the beginning, instead of categorizing us into a group of 30 or 40 students in a particular area, it allows us to intermix with each other. So that was the outcome, and I think it has had a very big impact. So some of the influential, I think, professors, I recall there was Radhakrishnan in mathematics, S.K. Sharma in materials. He used to teach us the structure, properties, and materials, and he was really, one of the fascinating teacher. The other names are Handa and Jyoti Mathur in computer science. So these were some very, very influential people, and I think they kind of subliminally may have had influenced my choice of a career eventually. The unique thing about I think BITS, at least at our time, so ours, you have to remember, ours was a 5-year program, because the higher secondary was only 11 years at that time. So we had 2 practice schools. One practice school was in the summer, which I did it at Bharat Electronics. That was interesting because we went to Bangalore, and it was a beautiful place at that time. And my second practice school, which was spending 6 months and working on a specific project, and that was, I think, a phenomenal experience for me from my education point of view. I think that kind of gave me some of the early germination of doing kind of advanced studies and research. And this was in at Department of Electronics in Delhi. In terms of my memories, I guess the iconic clock tower, the auditorium, where we, used to see the movies, but as well as have Ravi Shankar and Allah Rakha. I mean, very famous artist coming and giving us the concerts. The campus, the hostels and mess was one wonderful thing. The museum was one of those places where, but when you wanted to unwind and kind of be distracted from studies and things like that, it was a wonderful place to explore. And most importantly, I think the amazing group of 400 plus classmates from all over India. I think that was a great experience. After graduating from BITS, I was itching to just be done with education and studies, and I joined this company. I was selected. I think I was the only one selected by this company, which doesn't exist anymore. I think it exists in some other form, and it was called Tata Burroughs. So they only picked one BITSian in that year, and it was kind of an elitist company, but nevertheless, we can leave that for some other time. After working with them for 2 years as a COBOL programmer, I realized I needed to do something more with my life. So I decided to pursue a master's degree at this university called State University of New York at Stony Brook. And I had a sort of, I would say, life-changing experience there. Especially, I worked with a person called Art Bernstein, who's fairly well known in the early areas of computing, and had a very very important and transformation in terms of my career. Okay, and then I never, while being at BITS and while growing up in India, I never thought I'll end up becoming a teacher. And I don't know, as most of you know, sort of growing up in northern part of India, the teaching is a profession that is revered, but teaching is a profession that you don't want your children to get into. But nevertheless, I ended up coming to this university, and I've been here. And I've spent more than 30 years here. So, among my batchmates, I am infamous for having my name on this particular board. I don't know how many of you are aware of it, but apparently occasionally I am sent these pictures by various people. This particular photograph was sent by one of a BITSians, who's a faculty member at University of California at Merced, and he found this out, and we were serving on a committee, university-wide committee, UC-wide committee, and he just found that out. And many of my classmates probably blame me for their kind of GPAs and the grades, but I think I credit them for putting my name out there. So in terms of just what from my life experience, I guess what I have done is I really spent a significant chunk of my time in a beautiful campus, and really what I have been able to do is I have been able to transform from one beautiful campus to another beautiful campus. This is a campus at UC Santa Barbara. So we do have a tower here, but it doesn't have a clock. And the other difference is, I think BITS was kind of in a desert, surrounded by sand and desert, and here I'm surrounded by ocean and mountains. So that's a okay. With that, what I'm going to do is I'm going to spend maybe this is I just wanted to share with the picture of Santa Barbara, one of the pictures that I found. So this is Santa Barbara as a city. It's a small, relatively small city. It's tucked between the Pacific Ocean and the mountains, and there is a narrow strip of land, and that's where this beautiful place is. So what I'm going to do is I'm going to spend, maybe about 30 to 40 minutes. I should keep track of time. Maybe 30 minutes going over blockchains, not because, primarily because I think that's what I've been working on recently, among other things. And I think it is very, very, very interesting area. So my name is Divyakant, and I actually am also, generally, I think among my colleagues and professional community and the friends community, I am referred to as Divi. And you may think that this name or this christening may have occurred in BITS, but actually it occurred in my high school days. I had a friend who thought my name was too long, and he decided to start calling me by those 4 letters. So I just want to acknowledge some names. Throughout my career, I've been working with Professor Amr El-Abadi, and I think if Puneet probably would know that he actually sent the original invitation for this presentation not to me but to Professor Amr El-Abadi, and I think at that time Amr informed him that he's not the alumni of BITS, but I am, and that's how I ended up with the invitation. I just want to mention some of my, so I have a fair number of undergraduate students and undergraduate students working on my research lab. Okay, so let's talk a little bit about blockchains. So the area of blockchain has emerged as one of the promising technology, which is now being, originally it was kind of evolved in the context of cryptocurrency, but more recently it's being projected as one of the solutions for managing all kinds of data. So that you can think of cryptocurrency as a special form of data, where you're trying to maintain currency information or currency data. And now what people are starting to look at it is looking at the characteristics of blockchains in the context of maintaining different kinds of data. So what I'm going to do is I'm going to spend a little bit of time kind of explaining how blockchains work, and then I'm going to give you, I'm not going to get into more details as to what I have done in the area of blockchains, but I'm going to give you a kind of a formulation of some of the problems of some of the things that we are looking in the context of blockchains. And with that, I'm going to wrap up, and then perhaps we can have Q&A. Okay, so the question is, why is there so much interest in blockchain? Okay, so one thing is that unlike other data sources which are maintained kind of by huge organizations, for example, you have access to a Facebook application, but you really don't have access to the Facebook data itself, right? So in contrast to that, what happens in the blockchain context is the data itself is kind of exposed to everyone, whoever wants to look at it. So there is this notion of transparency. The other thing that blockchain provides is it provides you it provides you what is referred to as provenance, meaning you can see how the data has evolved over time. It is highly fault tolerant because you don't have one copy of data, but you have many copies of data scattered throughout the network. You also have a guarantee that the data is tamper proof, meaning it is immutable in the sense that people cannot go and modify the data as it exists. And finally, I think because it is tamper proof, there is some level of authenticity in the data. So these are from a data applications point of view, these are some of the very important properties. And typically what happens is, in the context of existing data sources, we rely on the organization or the enterprise that is managing the data, that they are going to provide us all these things. So we rely on having this trust on Facebook or trust on Google that they're managing the data in the way that they are saying, oh, it is, we are not going to do anything bad. Okay, so since blockchains emerged in the context of cryptocurrency, I think the best way to understand them is looking at the banking applications, the traditional banking applications, and see how compare and contrast to have a better understanding as to what blockchains are. So in the traditional banking system, you have, you basically are affiliated, you as a client kind of are a customer of a particular bank. And what happens is your interactions are obviously primarily with your bank, but occasionally you have to interact with if the interaction has to happen between two users who are from different banks, that interaction, that financial interaction has to happen or has to be managed via the respective banks. So you cannot, even though you have the money and you as Alice has the money and wants to give the money to Bob, but since the money is controlled by Alice's bank and Bob is associated with a different bank, then the banks have to get involved. Okay, so from a database and distributed computing perspective, in the banking system, the identities and signatures are sort of you and your signature, right? And in the electronic context, you have an ID, username, and password. So these are the instruments that you use to interact with the traditional banking system. There is a notion of a ledger. So in the financial applications, for each account, you basically maintain the ledger where all the transactions that have occurred on your account are saved. And this is saved in a database-like entity. Okay. And typically the thing that is sort of transacted on are these notion of a transaction, which allows you to move money from one identity to another. There is a notion of concurrency control and serializability, where you have to worry about when many people trying to operate on the same account happen. You have to make sure they are somehow synchronized, and this is typically backed by a transaction log for recovery purposes. Okay, and most importantly, the assumption is that this log that is being maintained is immutable and tamper-free, but this you have to rely on the bank as being the trusted entity that is providing that. Okay, so in 2008, there was a paper. It's a relatively short paper. It's a 6-page paper that was published. That actually didn't get published. That came into sort of being into the archives. And this is a person called Nakamoto who actually is not known as to who this person is, but he came up with a series of kind of techniques from cryptography, databases, distributed systems, and really put forward a proposal where he said that basically you can eliminate the bank and you can make the network as a repository of cryptocurrency information. Okay, so now what you have is there is not a single entity that is maintaining the information, but rather the network becomes the repository. Okay, and you as a user, you basically interact with this network to facilitate your transaction. So how does that happen? It's basically this idea of is referred to as a peer-to-peer electronic cash system. And now what we can do is we can kind of look at, sort of compare and contrast as to how different notions get translated over in this architecture. Okay, so the notion of identities and signatures is managed by this cryptography techniques called public-private key pairs. So you as a person has a public and a private key, and basically using this notion of key pairs, you can now manage your identities. Okay, so the ledger is the blockchain itself, and the transactions are moving bitcoins from one identity to another. There is a notion of, there is issue of concurrency control and serialization of transaction that is brought about by using this notion of mining and proof of work, which I'm going to explain in a moment. And the transaction log is the blockchain itself. Okay, and the log is persistent because it is replicated across the network node, so you cannot, it can't just be lost. And it is immutable and tamper-free, which is based on this notion of proof of work and the notion of hash pointers. Okay, so so let's just quickly look at the notion of public key and private key. So when I want to issue a check in this sort of Bitcoin framework, you basically take the document and use my private key to create an encrypted document, or a signed document, which is shown in the bottom of the picture. I guess I can use some laser pointer. All right. Okay, so that is the instrument. And on the receiving end, if somebody wants to verify the authenticity of my transaction, then basically they can look at the document and the public key and the signed instrument that I have provided, and they can very easily verify if it's a valid signature or it's invalid signature. Okay, so the idea is that basically the public key, private key becomes mathematically, it is hard to forge, or you can't create forged documents, but it is very easy to verify from a computational perspective. Okay. Now, so the way the cryptocurrency works is essentially what you're doing is in the cryptocurrency is you're moving money around. So the money is being transacted from one user identity to another user identity. So, for example, if Alice, who has some money and wants to give the money to Bob, what it does is basically kind of puts Bob's public key and its own. So he takes her money and identifies Bob through his public key and basically signs that instrument. And that instrument says that Alice is transferring some units of currency from Alice to Bob. Okay, and on the other side, Bob or anybody else can verify that indeed the Alice, this particular instrument is transferring money from Alice and Bob, because you have both the public key of both Bob and Alice. Okay, and this mechanism, this mechanism basically can be carried over transitively. So when Bob has the money and Bob wants to transfer the money to somebody else, he can basically take the instrument that he has and kind of combine it using the same technique of the public key of the new user as well as the secret key of Bob. Okay, so the big picture is that essentially what you can do is you can maintain the sequence of transfers that are happening in the cryptocurrency domain or in the electronic currency domain. So it's very different from our traditional money mechanism, where you really, you don't have a history of how the money goes from point A to point B, right? Here, what you have is, if you want to track down how the transitioning of the transfer of money has happened, you have a complete history of those transactions. So that's, I think, is a very powerful paradigm. So from a validation perspective, the other thing is, although I haven't showed you, but basically what happens is the units of currency is, so right now when you're dealing with real currency, you have to, when you give 500 rupees, so you can't just break it up into pieces. In the context of Bitcoin, you can actually do fractional allocations and still be able to keep track of how these fractional allocations came about. So you can do splitting and you can do merging. Okay, so there are some questions arises that if you start having this, combining these the history, how do you carry this history? I mean, what's going to happen is going to become very voluminous as the currency transfers from one person to the other, to the other, to the other. This can become very, very large. And how does Bitcoin or cryptocurrencies maintain that? The second thing is, this is all electronic. How do you prevent from, Bob doing spurious things, in the sense that, with using the same instrument, Bob can say, okay, here you can I give you this money to, you can make multiple copies of that money, and then you can start distributing to more people. So you have this problem of double spending, and you have to worry about that to make sure that doesn't happen. Okay, and so I am not going to talk about the combination function. All I will say is there is a cryptographic technique called SHA-256, which is used to basically, you take a long document and you can basically hash it into a fixed size bits, and that's how you can maintain this huge amount of information. So what I'm going to do is talk a little bit about how the double spending is prevented. Okay. and the issue of proof of work and mining, I'm going to also briefly touch upon. Okay, so we have to worry about double spending, and it's, what you have to recognize, the double spending is not possible in the context of a physical cash, because unless you have significant access to making forged currency, you can't just say, okay, I'm going to make multiple 500 rupees notes into many copies of that. But in the context of cryptocurrency, because these are electronic instruments, you can easily make multiple copies and you can start distributing them around. So the question is, how do you prevent this type of thing? Okay. So we need to, so basically what are the questions that arise in this context is, so in order to understand or do this double spending prevention, we need to have a better understanding of what is the ledger and how transactions come into being in this ledger, and what incentivizes the network nodes to become the keeper of this ledger. Okay, so why would the network become the repository for keeping this? Okay, so these are some of the questions that arise, and I'm going to try to answer briefly, give you a high level overview. So one thing is So I think let's not worry about that. So basically, a blockchain is kind of from a computer science point of view, is a a a linked list of transaction blocks that are linked together. That's what it is. Okay. So the question is, how do you prevent people not kind of manipulating this particular linked list? So the way it is prevented is by this notion of a hash pointer, and what this hash pointer is, that in every new block that is added, it basically maintains the hashed value, some hash computed value of the previous block is maintained along with the link that you're pointing to. Okay. So how does that prevent tampering? Well, so obviously, if you want to tamper with this ledger, so for example, what I'm showing here is that, let's say somebody modifies these two transactions which were actually just transfer of, let's say, $1,000 to $1,000,000. What that means is this particular block, the content of this block has changed. Okay, if the content of this block has changed, this hash is no longer going to correspond to the content of this particular block. What that means is this particular hash pointer has to be updated. Okay. Well, but if the but so if that by itself is not enough, because since hash is also part of the content, what if a person who's modifying or who's kind of tampering with this particular block is going to be responsible for not only modifying this, but modifying the entire sequence starting from here, because the hash is a part of the content of this block itself, right? So if this hash changes, then that means this hash is no longer valid, and sort of by transitivity, you have to go all the way to the end of the chain to modify all the blocks you have. Okay. So so what this means is we have to make sure that changing the content of the blocks is extremely hard, and that's, I think, is how you can maintain the tamper proofing of the blockchain. Okay, so the next thing is that when you have given a blockchain, and the question is you want to add new block of transactions, how do you decide which block of transaction is going to arrive? Okay, so this idea is based on, so what you have is, since there are many nodes involved in maintaining this blockchain, so let's say there are 100 people who are 100 network nodes who are maintaining this blockchain, then they all have to agree on what is going to be the next block, because they all are maintaining the same kind of replicated information. So there has to be a consensus among these 100 people to decide as to what is going to be the next block in the blockchain. Okay, so this idea of consensus has been around in the context of distributed computing, and typically the notion of consensus comes about in the context of if you have a set of nodes, and if these nodes are only kind of can suffer crash failures, then there is a protocol called Paxos which allows you to have consensus as long as you have the only majority of the nodes fail. There is also another model in which which is referred to as a Byzantine fault tolerance, where if the network nodes could be malicious, meaning you cannot trust them and they could be lying to each other, and in that environment you can reach a consensus as long as only 1/3 of the nodes are not lying. Now the problem is, even though these protocols are very, very very robust and very, very good, they cannot be used in the cryptocurrency domain, because the number of nodes have to be known in advance. Okay. Now, what you have to realize is, in the context of so I have to see. Okay, in the context of kind of an open system, such as a peer-to-peer computing, you don't know what is the total number of nodes in the system. All right, and the other thing is the number of nodes can be very large. So, so Nakamoto's basically replaced. So what Nakamoto's proposed was, he proposed this notion of proof of work. So what he did was, he replaced the notion of kind of consensus, which is typically achieved by communication among the nodes, by doing computation. So what the idea of proof of work is that, so everyone who's maintaining this blockchain and wants to add its block to the blockchain, what they have to do is they all have to compete with each other to solve a certain kind of a puzzle. Okay, so this is a cryptographic puzzle, and everybody kind of is in a race to solve this puzzle. Okay, so once the node who has solved the puzzle and demonstrates to other nodes, that I have a solution, then basically that person emerges as a winner, and that person's block becomes the next block in the blockchain. So that's kind of is the idea. And if you're interested, you guys should read up more on this. But that's basically it. So essentially, you have a mining node, and so the big blue dot is the node that is maintaining the blockchain, and it basically collects the transactions that are happening, and it creates a block. And the reason this particular miner is interested in performing this activity is because, as a result of this mining, it is going to be given some reward, which is going to be the currency itself. So this is the idea of this is how new bitcoins come into being, and that reward is going to be, if this block is added to the blockchain, then this reward is going to be credited to this particular miner. Okay, so kind of going a little bit more in the details, what happens is, essentially what you do is, you have these block of transactions, and there is some the header information, and in particular what you're trying to solve is a puzzle where you have to make sure you have to find a hash value. you have to create your content such that the hash value matches a certain kind of a bit pattern. So essentially what you can do is, there is this extra field called nonce, and by manipulating this extra field, what you are trying to do is, you are trying to create this data in such a way so that this particular hashed value, computed value, has a certain bit pattern. So that's basically the idea. The bit pattern is that, the hash value should have 6 leading zeros or something like that, or 20 leading zeros. That's what the difficulty bits are considered. Okay? And this is so this is, so what you may ask is that whatever bit pattern that emerges after the hashing, that bit pattern should show those many, that there must be this particular part of the pattern should have a specific characteristic. So typically you should have, let's say, some leading zeros. Okay. Now this problem can be shown cryptographically. It's a very hard problem, and it requires essentially doing an exhaustive search. Okay. So it's not easily, you cannot easily kind of come up with a solution, and that's how Bitcoin mechanism works. Okay. So I'm just going to mention that it cannot be pre-computed. So because in order to come up with the bit pattern, you have to have the content of the block ready, and it depends on the current block of transaction and previous blocks. And it cannot be stolen because the reward transaction is signed to the public key of the miner. So somebody cannot hijack it. Okay. So with this, what happens is both the problem of double spending and kind of is solved. So you basically, what you are doing is you are linearizing the addition of blocks into the blockchain. So the first person who wins the proof, the mining competition is the next one to go. So now you have a very predefined mechanism by which the evolution happened. Now what one of the things that can happen is that you could have two kind of simultaneous or forking of the bit of the ledger, but I am going to not get into that. Basically it's resolved in a probabilistic manner, in the sense that if you have forking in the blockchain, then the longest chain becomes dominant and the short chains kind of disappear. So let me just talk a little bit about what are the problems with Bitcoin. So the technology is very, very interesting, but the problem with it is that it has the transaction latency is very high. So this proof of work that we are talking about requires a huge amount of computation, and it can take a long time to come up with the answers. Okay, there is the number of transactions in the current scheme of things that can be executed in such a system is somewhere between 3 to 7 transactions per second, and the addition of a block happens every 10 minutes. So people generally think that this is too slow for any meaningful application. So if you want to go away from cryptocurrency to any other data-rich applications, these numbers are too small compared to the traditional techniques of transaction processing system. Okay, so one idea is you could perhaps increase the size of the blocks to improve the latency and throughput issue in the context of Bitcoins, or decrease the block interval. But that both of these techniques suffer from some problems. Essentially, there is an issue of fairness, and if you reduce the block interval, then there are too many forks and so on. So one idea, and I think I'm going to stop at that. One idea would be is that that is actually used a lot. This particular notion is used a lot in the context of large scale systems, is what is referred to as sharding or partitioning. So what you can do is, what you can think of it as, you can basically, you have your blockchain, and instead of maintaining it as, you can think of each transaction block to be sharded into different sort of parts of the network. So now what you have is, instead of having a single network, you have a network which is yellow, blue, red, and green. Okay, so now what you can do is, basically, as you start partitioning the network, you can easily kind of increase the throughput in the system by the number of partitions you have. So if you had a single network, you had a certain throughput, and if you have 4 different colors, then you can make it 4x. Okay, so that's the general idea. Okay, so conceptually, what that means is that basically, if you have interactions of users within your network, then it's fine. So, if Alice and Bob are in the blue network, they can do there. And if Peter and Paul are in the green network, they can interact here. But occasionally you might have a situation where you have to worry about these cross shard transactions. So meaning Alice could be in the blue network and Bob could be in the red network. So now the question is, how do you perform a transfer through these different parts of through these different shards? So this is referred to as a cross shard transactions. And what that means is you have to also worry about, if you're going to do a transfer money from here, from the blue network to somebody who's in the red network. Now what that means is you have to be careful that you don't take the money out and don't put the money in here. Or the other way, think about it, is the issue that you have to worry about. You can't have a situation where the money has been deposited but the money has not been taken out. Okay, so these are the problems. And what this requires is you need to ensure that this interaction is atomic across these two different blockchains. Okay, so I hope this problem is clear to everyone. So let me just explain the problem, and I'm not going to give you the solution. I'm going to just kind of tell you why is it a hard problem. So in order to understand that, let's think of this cross-chain transaction as follows. So you have two blockchains. One is a Bitcoin and one is another cryptocurrency called Ethereum. Okay. You have Alice sitting here with some number of Bitcoins, and you have Bob sitting on the other side with some number of Ethereum. Okay. Now let's say that Bob and Alice have agreed to exchange this money with each other, meaning Bob is agreed to give Y Ethereum to Alice if Alice gives X Bitcoins to Bob. Okay, so the transfer has to happen is that Bob is willing to give Y Ethers to Alice as long as Alice is going to give X Bitcoins. Okay, so this interaction is referred to as an atomic cross-chain commitment protocol. And you can see the complexity is that you have to, since these are two different blockchains, right? And they're not synchronized with each other, they're completely asynchronous. So you have to worry about situations. What can happen is Alice might give the Bitcoins, but then Bob might never pay the Ethers. Okay, and vice versa. So you need to come up with a protocol or mechanism so that both Alice and Bob keep their ends of the bargain, right? So it should happen that either both of them do the transfer or none of them do the transfer. So this notion is referred to as atomic commitment in the context of databases. Okay. All right. So I am. So I don't know. Can someone tell me how are we doing with respect to time? Because I think I just want to let me wrap up with this. So this is an interesting problem. There was a solution that came in. That was proposed actually by as a blog entry in 2011 or 12, and this is from Nolan. And in 2018, there was a paper by Hurley which formalized this problem. Okay. The point I want to make from here is that, so it's been like, so the original proposal or protocol, a simple solution was proposed in 2012. In 2018, there was a formal kind of paper that was published in one of the conferences called Principles of Database Distributed Computing. And this particular paper formalizes this notion, this protocol. The problem with that solution is that it does not work all the time. Okay, so in particular, what happens is that there is a possibility that the interaction is not completed if something goes wrong. Okay, so I mean, effectively, what I'm saying is the solution that has been proposed and that kind of was published is not completely correct. Okay, so I'm going to skip over these slides, guys, because I think otherwise. Okay, so what I want to do is essentially I wanted to just say is that in that work it took almost like 5-6 years, but what the solution what we have is not complete and is not completely correct. And so we had started working on this problem in a couple, last couple of years with one of our PhD students. And we came up with a solution which can be shown to be correct in spite of all the violations that might happen. And this appeared in VLDB 2020. And the basic idea is it uses the notion of another. So it basically uses the abstract idea of atomic commitment in distributed computing and databases. And what happens is these atomic commitment of distributed transactions requires a mechanism called a coordinator. Now the problem is the coordinator in the traditional setting is a single node. And what we do is we replace that coordinator from it being a single node to a blockchain itself. So with notion of using a witness, a blockchain to be the witness or the coordinator of the atomic swap. So this is the technique that we have used, and this appeared in one of the conferences and databases called VLDB 2020. Okay, so what I'm going to do is I'm going to say that so the Bitcoin and blockchain is very interesting, but they are actually not completely very useful for using it in other applications. In particular, the throughput and latency is not good enough for any data-centric application. So the Bitcoin and blockchain is referred to as a permissionless system. There is a notion of permission blockchain, which consists of a set of nodes. So what you do is instead of using an open network concept, you make it a closed network concept. So you restrict the number of nodes in the system to much fewer, but you know the identities of these networks. So in some sense, what you're saying is instead of the blockchain being open to all, what you do is you basically make it restricted to some number of entities. So this is referred to as a permission blockchain. And the idea is you run the blockchain among a set of nodes or identified participants. Now, the reason of the issue of trust still remains, that even though these known identities are working together, they do not trust each other. Okay, so you have to still maintain all the characteristics of the maliciousness. you have to maintain the characteristics of making sure that there is a consensus in the system, because you are communicating with each other, but you never know who's lying and who's telling you the truth. So in this environment, the question is, how do you achieve that? So this, I think, has emerged as a very viable solution in the context of blockchain, and this is referred to as a permission blockchain. And one of the names you might have heard is something called a technology called Hyperledger, and IBM, I think, is running a consortium building that technology, and that's, I think, is seems like a very promising arena. So in the context of so the reason these permission blockchains come into play is that they can be used in the context of supply chain type of activities. So so I think I'm going to skip this, but basically the supply chain is by using what happens is when you have a source and you want to track kind of the activities associated with that source, and when many entities are involved, you have to worry about lots of things happening. So for example, Dolby is a company which creates intellectual property. So they basically design chips for various kind that get fabricated in foundries all over the world, and then these foundry manufacturers basically ship the chips to different types of companies that use it in building their devices, and then it goes to the retailers and so on. So what happens is, from Dolby's point of view, they have the way they earn money is they earn money based on the royalties of their intellectual property. Okay, so it becomes very difficult to track down, because all this, there are so many actors involved in this. In order for Dolby to figure out what should be who all should be paying them up, it becomes a very hard problem. So it is envisioned that something like a blockchain technology can be very useful, because blockchain has the the issue of provenance. So for example, at the end user case, you can basically verify or track down as to where the source of your kind of integrate the IP is coming from. So that's kind of is the promise of blockchain, and many systems are starting to explore this idea. They are also, for example, so Walmart uses the notion of blockchain, and so in the context of their supply chain, for their food sources, so they can track down exactly if there is something goes wrong, they can track down where the contamination came from. Okay, so I'm going to kind of tell you what kind of things we are doing in the context of permission blockchain. So one of the issue comes in the context of blockchain is the issue of performance. So I think if you execute transactions one after the other, it's extremely slow. So what you want to be able to do is, in the context of permission blockchain, you want to find out how you can execute multiple transactions in parallel. So instead of doing consensus on a single transaction, you want to be able to execute these transactions in parallel. The other thing is the issue of confidentiality. So what happens is, when you have multiple enterprises involved in a supply chain type of activities, you still want to maintain sort of some notion of confidentiality, in the sense that, for example, my private transactions should not be, even though they are on the blockchain, should not be exposed to everyone else. So the question is, how do you facilitate that? And you can also see that at the extreme, you have shared transactions and private transaction, but you could also have subgroups who want to maintain confidentiality. So you might have, if you have a blockchain involving enterprise A, B, and C, but there might be some interaction between enterprise A and B, and they want to keep that private from C. So how do you maintain that? The issue of scalability is the same thing, that you want to scale the system. And here, I think the scalability is, again, based on this notion of partitioning the data or sharding the data. And finally, there is this notion of verifiability that comes about because of some regulations. You want to be able to verify certain properties about these platforms. So these are some of the problems that we are working in, and some of our students are looking into that. Okay. So let me just close with some kind of discussion items that we can take on. So in the context of permissionless systems, the Bitcoin, there are many issues. Is that the amount of energy that is consumed to do the proof of work or mining is really extremely high. Okay, the whole idea of blockchain emerged so that you wanted to eliminate the powerful players from kind of monopolizing the system. So the whole idea was you wanted to decentralize the maintenance of data in the network. But what has happened is, at least in the current context, what happens is there is a handful of miners who control the progress of the Bitcoin blockchain. So in some sense, what we wanted to eliminate, the bank, has been eliminated by a kind of the mafia of miners. Okay. There is also the issue of security, because I think your individual is vulnerable to the security, because if you lose your public key, private key type of a system entity, then you obviously become vulnerable for attacks. The Bitcoin provides you extreme distribution, but the question is it really worth it? There is extreme redundancy, meaning there is many copies of the data, and this much of redundancy, is it really necessary? And the other thing is, there is also some concern, is that you can use the Bitcoin for bad activity, and what are the social consequences. And in a larger context, I think we all have to start worrying about what are the social consequences of the extreme decentralization that is occurring in the network. I'm sorry to have rushed through with this, but hopefully I think you get an idea of the Bitcoin stuff. So I'm going to stop sharing, and I'm going to kind of how do I do this? Okay, I'm going to stop sharing, and I'm going to hand it over to Sarthak or Puneet to take over from here.
Thank you, sir, for such a wonderful presentation. It would be great if you now head over to the question section on AirMeet.
So how do I do that?
Sir, open Google Chrome.
Okay, no. I think I can see the questions.
Okay.
So Ameya is asked. So okay, I'm sorry, guys. I wasn't. So this platform is a little bit Why the reward for solving block is decreasing year by year. In 2012, the reward was 25 BTC and 20. Okay, so one of the thing is that happens is the reason the reward gets smaller and smaller is because your infrastructure is also improving. So the amount of effort it took in 2012 to solve the same problem, it can be solved much faster. So that's kind of is the reason for the reduction in the amount of compensation. Okay. Okay. I am not. So I guess there is a question from Amaya Deshmukh. What are your thoughts on the recent cryptocurrency bill, which is going to be discussed in the upcoming parliament session? So I am not aware of what's happening in that context. So you'll have to. Can they speak? No.
No, actually, only the speakers can speak. The audience can't speak.
Okay. Okay. All right. So I don't know. I think I'm not sure. And even if I knew about it, I'm not the person who is into the regulations, and so I think I'm not a policy person per se. I am a technologist, and I think I might not have the perceptive. I probably may not have the understanding from a regulation or policy point of view. So that's what I would say. So how does modifying initial nodes impact the hash values of successive transaction? So Rohan, the what happens is that the hash pointer itself is a content that you maintain in the block, right? Now, once you change the hash pointer, so effectively what you have done is you have modified the content of the block. So that's going to impact the hash pointer of the subsequent block. So that's kind of is the idea. What are your thoughts on the entire Ethereum development ecosystem? Does it have the potential to be the next Bitcoin, so to say? So, what I understand, the Ethereum ecosystem is much more powerful because it provides kind of a language mechanism to go beyond cryptocurrency. So they have smart contracts programming language, and I think Ethereum. I'm not going to speculate on the currency's importance, but I think Ethereum is going to have an impact more in that context, in the sense that you can do much more complex asset manipulation than just a simple cryptocurrency. So right now, Bitcoin, all it does is you can manipulate essentially money amounts, but there is no reason why you cannot maintain more complex asset classes, cars, houses, and so on. So I think that's where Ethereum is going to play a role. So I don't know how, I don't have a good answer. What makes Bitcoin different from other cryptocurrency like Ethereum and Ripple? So one of the things is Bitcoin is one of the early entrant, right? So I think what makes Bitcoin different is that it has a wider adoption, meaning there are large number of people who have started using it, and the Ethereum and Ripple are the late entrant, so it takes some time for them to reach that level of kind of awareness. But I think from a technology point of view, which is what I am interested in, I think I look at it The differences between these system is the Bitcoin was, is if you think from a technology standpoint, I think it is very uh, I I mean, it's a straightforward adaptation or implementation of Nakamoto's protocol. Ethereum started thinking much more sophisticated way, and Ripple, I think, if I'm not wrong, they're trying to overcome some of the deficiencies of Bitcoin. So, for example, I think the proof of work is considered extremely, you know, it's very resource intensive activity. So I think Ripple uses a different technique for reaching consensus. I think that's what I know. Sir, can cryptocurrencies replace normal currencies worldwide? What are the advantages of using a cryptocurrency like Bitcoin? So let me I guess so so this is a difficult thing to kind of answer, because a new technology not does not necessarily replace what exists, what is already being used. So for example, the to a certain extent, I mean, the cell phones or mobile phones have not replaced, at least in the United States, the traditional phone system. For example, they coexist. But more importantly, what's going to happen is the currents, the kind of what is going to be the future of cryptocurrency is going to be very heavily weighted upon what are the policy decisions that are made, because currency is an extremely, as you know, from a nation's perspective, it is an extremely important instrument that they have to control, right? And the question is, so for example, I think uh, if I'm not wrong, I think countries like China and all had initially completely banned the activities in the context of cryptocurrency, because I think China likes to maintain a very strict control on its monetary policy. So the larger question is whether this is going to happen or not is going to depend upon how the reserve banks of the world are going to be dealing with the issue of currencies. From our point of view, I think what we should be thinking about as engineers and technologists is not so much whether this is going to be useful for cryptocurrency or money context, but I think the question that we should be asking is from a technology standpoint, is it useful in other context? I think is a much better question to answer. We should not. I mean, I'm not interested in whether cryptocurrency makes it or not. That's what I'm interested is the underlying platform, the underlying infrastructure, and the underlying protocols. Is there something useful about them that I could use it in the context of other application? And that I'm going to tell you that, for example, if you go back, you guys you probably were not born, but if you go back when I don't know how many of you know, there was a notion of there was a company called Napster, right, in the early 2000s. So they were a peer-to-peer computing platform for music sharing, right? So that emerged, and effectively that music sharing was, it was clamped down by the large music companies, because they basically, at least in the United States, they basically said that this was copyright violation and so on, and that service got disbanded. Okay, so in some sense, nothing happened here. But what came up from Napster was there were fundamental kind of solutions that emerged, the P2P concept that emerged, that actually many of them transferred over in the context of data center technologies. So I think that's, what we should be thinking about is not so much the application itself, but we should be thinking about looking at the underlying kind of concepts and technologies and the solutions and that is buried deep there in the context of that application. And the question is there a use of those components in the context of another application? So that's, I think, is what I am going to say about what might happen to cryptocurrency or not. Okay, is there... Okay, Sarthak, you...
Okay, sir. So, thank you, sir, for sparing your valuable time from your busy schedule for our talk.
Yeah, so I
And
woke up at 5 o'clock in the morning.
oh, thank you so much, sir.
Okay.
And before proceeding towards the end, we will be playing a short video. And thank you everyone for tuning in with us. Thank you everyone, and have a
So
nice
last,
day.
so last time when you played the video, I didn't see the video.
We are going. Okay. I don't know about that.
Okay, let's see. All right.